Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're going to talk about Copenhagen Suborbital going small. They are making a smaller engine, so let's dive deep into it. Now, just in case you are unaware of Copenhagen Suborbital, let's take a brief loop. So they are the only crowd-funded crewed space rocket company, meaning this company is building a rocket. Why? Just because they can. Are they planning to launch satellite on it? No. They have one goal, singular goal. The goal is to put a person on an amateur rocket that crosses the Kármán line. Basically, exactly like a New Glenn rocket. Not New Glenn, basically. Okay, I do not want to share the name of that rocket anymore. It's like, it looks phallic. Basically, cross the Kármán line, same thing. Jeff Bezos' rocket. And then that's the whole point. Do the same thing, only with one person and built on an amateur rocket. Now, what does amateur rocket means here? Amateur and professional are very clear distinctions, so to say. So whenever you are saying professional, it actually has to mean only one thing. That thing is that you are getting paid for your work. Meaning, if I'm running YouTube channel and I'm getting paid from YouTube and that income is actually matters to me, I'm professional. It does not matter the quality. Professional, we say also to use it as a mark of quality and all that, but that's add-on. The core is, are you getting paid or not? Then we come to amateur. Amateur does not mean inferior or something like that. It simply means you are not getting paid for it. It could be a hobby to you. So it's one of those core vector that you have to understand. They are working on amateur level, meaning they are not getting paid for it. Of course, they are collecting money from crowdfunding, but it's not their main job. Most of them have first job, and then this is their second job that they are doing. And of course, they do hire students. They require universities do require you to have some actual apprenticeship and all that jazz. They do help them in those sort of scenario. Those will be like, hey, apprentice are working. But overall, ecosystem wise, they are amateur company. Now, common public can get access to it. Now, be mindful, because it's a crowdfunding thing, as a gift to the people who are actually paying them for the expenses, is they're gonna get completely behind the scene access without any limitation. And after a certain while, we also get a very good look behind the scene, what exactly is happening, who is all working on it. And it's the first time ever that has ever happened. So it's a really good thing. And they are based on Denmark from 2011. They are old, as in 12 years old and counting. Now you may be like, why the heck go through so much hassle that not only you do first job, you do a second job, do a crowdsourcing firm, and then of course keep collecting and keep updating them and keep building rockets in 2011, 2012, 2013, 2014, 2016, 2018. Of course, they have actually built large rockets and that have actually flown. So they know what they are talking about. So question is why? Well, the answer is very simple. Why not? If you go into their own website, they have a very interesting line, because it's there. And I like this approach where it's like, to be fair, like, why else do we do anything? So it's there. It's like, we can do it. People go to Mount Everest. Some people want to go to Kármán line. And if this company succeeds, depending on timeline, you could be looking at like fourth or fifth country that achieved space flight. That would be bonkers. That Denmark randomly just becomes a country that achieves space flight before ESA. So this would be interesting. Now, be mindful, right now India also is on track, and our Gaganyaan project could yield results before them. So what was the problem? Well, problem is they're not ISRO or SpaceX or ESA. They do not have what you call deep pockets, or any pocket for that matter. So their resource, man hours, they are very, very limited. Whenever you say NASA or SpaceX or ESA, they generally have a very ginormous warehouse that is working behind them. Like, behind the scene, there is more than enough competent people with competent tool and a place to work safely that they are getting paid to do, is that they can get stuff done. So this company does not have that luxury. So they designed a BPM 100 engine, which was more or less like Falcon 1 has one engine, something similar to that. And they designed it on paper, everything on CAD system, simulated it, all that jazz. And then they started to build it, and it was taking too much money. Too much money. It was like too costly. And in-house facility, basically all the workshop that they have acquired, flat out could not work on it. That was creating a very serious hassle. The diameter of the tools required to deal with this, it was too huge, meaning their lathe was not large enough. Their milling table was not does not have enough travel to take care of all of that. So simply mean they had to do what we call external order. That created more lead time, meaning even if they have like, hey, can you just mill this ring out, and the ring is perfectly known, the dimension does not need to be changed, you just completely creating the CAD, sending the CAD to the company, dealing a finance to with that, then them actually building it, then they're actually packaging it, then shipping it. All of that was taking very long amount of time. So that's why if you have following their channel for a very serious amount of time, they had like some updates were very quick, like parachutes, tanks, they were keep getting done. But the engine, they were like engine, no updates were. That's why the lead times were brutal. And it also created a paradox where they were stuck with slower iteration, meaning they built the whole thing and they're like, oh, this will not work because of this, okay, now let's redo it again. They had to wait. So this created a very serious limitation with their BPM 100 engine. So this is Merlin 1D and this is what they are building. So they're actually trying to build a competent engine here. And so now going from basically SpaceX Falcon 1 rocket design, they are going more towards to Electron rockets design where they have multi-engine. So they built BPM25 engine. Now this engine, they have to go multi-engine. That's the side effect. Consequence would be plumbing. That's absolutely. However, there is another aspect. Is like how the heck they're gonna pressurize this puppy. I have seen them taking two approaches. Approach number one is pressurizing the system, pressure-fed engines. If you are only doing carbon line, it actually makes sense. They are not going at orbital velocity, so it can work, and it could even have a self-fulfilling what you call positive feedback loop, where the higher accelerate you do, the more fluid gets pumped down. The it can have a positive feedback, so you can actually do it. You're not going to go very far or very fast, but that's not the end game. So it can be done. Another option is electric turbo pump. That's why I said it's going more towards electron rocket. There is another company that is designing and selling electro turbo pumps for other small satellite rocket launch vehicles. So they also are working with Copenhagen to basically a sort of testing bed, so to say. So that will become more complex. So again, they could have a design where they have just one giant turbo pump giving fuel and fluids to all of them, or it could be multiple small ones. Let's see what happens. But the biggest benefit of this BPM25 is the banana for scale. That means everything can be built in-house, meaning this whole thing can be built in themselves. The lathe can handle it, the milling machine can handle it, and they have built a surprisingly good, competent frequency controlled welding systems that can weld these things to like aerospace grade, and they can do it in-house. That means going from a block of material to actual engine is surprisingly quick. Given the fact that nobody is working 24/7 into this, it's surprisingly quick. And after it goes boom, they can iterate it very quickly, because again, it will go boom. It's one of those things that you build it, you boom it, you build it, you boom it, you build it, then it works. So the quicker turnaround will be drastically expedite their progress. And iteration is also, because again, if all the tools you need to building this you already have, heck, just by if you are like, hey, on this date we're gonna do trial, you may build 2 or 3 engines with multiple variation just to test it out. So this is their BPM25 engine. Now, what are the pros and cons of the thing? Well, plumbing would be a brutal challenge. That's fact. Having 5 engine plumbing, that's not easy. Let's just put it that way. And they will have to endure what we classify as more throttling complexity. Meaning, whenever you're talking about engine has an envelope, so to say. So if people are saying like, why don't we just deep throttle engines? They become unstable. For example, if you looking into their BPM 100, if they throttle it down below a certain point, it will have what we call combustion instability, meaning it's gonna go boom. So that creates a serious threshold. So how do you balance like multiple engines? Well, actually helps you in one way. Of course, it's a complex thing in plumbing regard. Where do you have valves? How many valves do you have? How do you control each valve? So that is the complexity part. However, you do get the benefit, meaning let's say this engine, they build the engine, the engines are like, let's say each engine only has 25% throttle value and you require 50% throttle value. You could be like, hey, what about if I just turn off one engine? That would be far better to do rather than just putting engines into what we call unstable zones. So if you're like, hey, once the fuel is starting to drain, the rocket is getting too light and they had to reduce the throttle in order to keep the G loads under control, they could be like, hey, center engine turn off, or they could be like outer engines, 2 engines shut off. All of those things become possible, meaning each engine itself will always be at optimum combustion ratio. So that's actually desirable. Yes, complexity is the side effect, benefit is better control. operational envelope of each engine is maintained. In-house manufacturing, meaning they can actually do the testing and do it multiple times, rather than be like all the limited amount of money that they are getting, they cannot just lol that money. So they have to do multiple testing. But if they can do multiple testing in-house, they can do far more iteration without costing too much. Iterating into all that is there, and they will get higher control thrust vector, meaning in the single engine design, they knew for a fact that they have to have very complex gimbal, 2-axis gimbal, meaning 2-axis gimbal, something like this. 2-axis gimbal they had to have, but it will not be able to correct rolling, meaning you start to spin, it cannot be helped with this. However, if they have multiple engine, they can control with that. So in a previous design, they had to have cold gas thrusters in order to compensate for it. Here, it's no longer necessary. They can still add it just to give more control vector, but it's not necessary because it can control rotation. Having this many engines gives you much finer control. Basically, your control authority is exponentially higher. And they do not even have to worry about the export control and dual use intellectual property kind of hassle thing. Now, what is export control? Well, every country takes rockets seriously. Why? Rockets and ICBM, they are the same cousin, so to say. So if you know how to build a rocket, actual good rocket, you know how to build ICBM. Flat out. Fundamentally, they are the same thing. Of course, you may not know how to make it that robust that it can withstand, like, some ICBM interceptors go up to 100 G, and some ICBM can launch at bonker speed of 25 Gs. That's like, of course, that's a completely different thing. However, ICBM does not need to be that level. It does not need to be Minuteman level caliber to cause destruction or harm. That's for that reason, every country takes very serious precaution. So even if a country, let's say if they are in Denmark, they're going to some other country that is close by, and they're like Finland or Sweden or something like that, and they're like, hey, can you machine this? Company would be like, awesome. But the moment company will get wait a minute, this is the engine part, they will get a call from their own government. It's like, why are you building rocket parts? So it becomes a hassle. Can it be done? Of course, they were trying to do it. It's just like too much hassle, time wastage. So if everything becomes inside one roof, they can like, hey, this is what we are doing. Look at it, done. Don't worry about it. And intellectual property, like USA have the what we call ITAR regulations. It's a hassle. That's why you never see the actual photographs of modern rockets injector plates. That's they are very serious about. Nozzle, look into it. Turbopumps, look into it. Injector plate, no sir, no. So these are the pros and cons that they're going to gain if they go to multi-engine configuration. They can make it quicker. They will get much more control authority. Each engine itself will work inside their optimum value far longer, rather than like reaching an unstable point. So there are a lot of pros and cons with this. Now, this is a great system. Like this was the cold gas thruster that we are talking about. So this is the first time in humanity that we are getting to see behind the doors. Basically, right now we are having a close look with what SpaceX is doing. But here's the deal: we do not know what's going behind the door. We are seeing the final products. Oh, they changed this. Why did they change it? What was the pros and cons of that? We do not know. For example, in the early days, everybody knew Raptor is going to use electrical spark igniter. Okay, that makes sense. And now they're using still something electrical, but it's no longer spark igniter. So what is it? I have no idea. Nobody has any idea. They're like, that's the secret sauce. It's like, how exactly are you igniting the rocket? And igniting a rocket is a hard thing. So we don't know. Maybe it has a freaking microwave emitter or something like that. We do not know. This is the first time you're seeing a rocket being built from scratch and everything is open for public. So this is a really good tool to learn full-scale rocket development. This is the fuel tank that they are building. How did they weld it? That's the biggest issue. Whenever you are talking about metal itself is like, I got this, fam. How the heck you weld it, that's far more difficult than you would realize. Watch them and you will understand, oh, that's why they have to do this. Like, for example, when they are machining parts, each part is itself a part. You have to attach them. How do you attach them? They had to learn the hard way. It's like, oh, even in an engine, even if you have adaptive cooling, you may need to give what we call expansion room, where it can expand and contract without going kaboom. So this is really, really awesome. So why they are doing it, what they are doing it, we are getting to know real time. Meaning I was seeing them when they are experimenting with cold gas thruster. I am seeing them when they are experimenting with new lathe machine and new milling designs and all that. I am seeing them when they are actually figuring out how the heck they're gonna weld it, how the heck they're gonna pressure test it. So it's really good learning knowledge. So it's one of the best study material I can recommend to anyone who wants to get into engineering as of now. Flat out, there is nothing that even comes close, because most of you engineer who are studying, they know what PID means, controls and all that loop. But here's the deal, that's one thing you do. You may be even top class basically in that. You can clear all exams on that. But do you know how to actually take your idea, make into a real thing? That's a ludicrously complex thing. And that's the whole reason Oppenheimer is so respected. It's like everybody had the idea, but how the heck you make it into, okay, we have the idea to actually going kaboom. That took serious amount of effort. Like the most complex part that they had to deal with was, again, everything was complex, let that be very clear. But the hardest thing was like what we call explosive lensing. So how do you make sure everything goes properly? That was the hard part. Again, they are also facing it. Their design decision, again, as an engineer you have to know, because there is no what we call one size fits all. Everything is right tool for the right job. So the very thing that made SpaceX was not something that's going to work with them. So the very thing that works with Electron rocket may work with them, may not work with them. So they had to do all these things in real time. Many students are going there and volunteering their services, and that's actually a good thing. You can actually get real world experience. So it's a really good thing, and I really love the idea that they are slowly making rockets into something that, you know, things people can build. Like in the early days, as in like 1970s, if you had talked to anyone who's like, "Hey, I'm going to build CNC machine," people would have laughed you out of the room. But here's the deal: now we do not even take it seriously. It's like, oh, you know, a 14-year-old boy builds CNC machine in summer vacation. 3D print. A 12-year-old boy builds a 3D printer in home. That nobody cares about it. Oh, another 11-year-old boy builds a fusion reactor in home. Nobody cares about it. That's awesome. That's what we want in humanity. It's just like somebody's like, you know what? A summer vacation, let's build a rocket. Of course, I'm exaggerating, but here's the deal. Back in the 70s, talk to them, anyone where it's like, oh, kids would be putting together a 3D printer, they would have laughed you out of the room. Well, like, dude, please give your supplier name, man. I also want that supply. But here's the deal, we don't care about it. And that's what they are doing. And I like this. This is awesome. It's like, hey, just build the damn thing. Oh, this is a tank. This is how you have to test it. This is how you will know whether it will work or it will go boom. These are the, you know, gotchas. They have gone through all of that. Everything is available for public. That's awesome. I like it. So this was my presentation on Copenhagen suborbital going small. So hopefully you have liked it, learned from it. In that case, please hit the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.